In this video, we'll discuss applications of first-order ordinary differential equations. First, we're going to review 5 methods for solving first-order ODEs. And then we're going to talk about variation. Variation is going to allow us to translate English sentences into differential equations. I would say that is one of the most important parts of this lesson because even though it's a very simple concept, it is the part of the applications of first order ODEs that students tend to struggle with most. Most of the time I can talk to students about how to solve the differential equation and they're fine, but they might struggle with reading that problem statement and setting up the appropriate differential equation. So we will talk about how we translate sentences into differential equations. Then we'll look at a number of well-known application problems. And then we'll do at least one example, maybe 2 examples, depending on how much time we have. So let's start with our 5 methods for solving first-order ODEs. We talked about separable differential equations. So if a differential equation can be written in this form, the derivative equals a function of the independent variable times a function of the dependent variable. You can get all the variables or all the similar variables on one side, and then you can anti-differentiate. So in this case, we might divide by g of y and multiply by dx, and then anti-differentiate both sides to solve. That's the easiest of our methods. And this method comes up over and over again in this course and in other courses if you take partial differential equations. So it's really important that you know how to solve a separable differential equation. Another method that comes up repeatedly is the method for solving first order linear ordinary differential equations. And here we want to use an integrating factor to solve. If the differential equation looks like this, or it can be written like this, then we multiply by an integrating factor. It's e to the integral of p of x dx, and that transforms the left-hand side into the derivative of the dependent variable times the integrating factor, and then you're just 2 steps away from getting that dependent variable by itself. You just anti-differentiate and divide. So both of these methods are really important. After studying these, we studied homogeneous polar differential equations. The homogeneous polar differential equations can be written in a number of different forms. One of the forms is this. This is typically the form that we solve from. If that derivative of y with respect to x can be written as a function of y over x only, then the differential equation is homogeneous polar. Another way that you could write a homogeneous polar equation is like this. dy dx equals some function of x and y over some other function of x and y. If the differential equation can be written like this, where the function in the numerator and the function in the denominator are both homogeneous functions of the same degree, in that case, the differential equation is homogeneous polar. And remember, a function is homogeneous if you can replace the x with tx and replace the y with ty, and you get t to some power times the original function back after some simplification. So you plug these in and you do some algebra, and then you are able to factor out that power of t. This power here, that's the degree of that homogeneous function. So if this is a homogeneous function of degree n and so is this, then the differential equation is homogeneous polar, and that means this right-hand side can be written as a function of y over x, and then we'll solve with a substitution. Another way homogeneous polar differential equations can be written is like this. And this is where m and n are homogeneous functions of the same degree. So that's what we've got here. Now you solve these by doing the following. You let v equal y divided by x, and then you can take this form of that homogeneous polar differential equation and you can write it as a separable differential equation in v and x. So you solve the separable equation and then you back substitute to write a differential equation, or write a solution down, excuse me, involving y and x. And then if you can solve for y, you do. You call that an explicit solution. If you can't, you don't, and you call that an implicit solution. Now that was a differential equation that can be solved by a substitution. You make the substitution, and then the resulting differential equation is separable. So the substitution reduces the homogeneous polar equation into a separable equation. You solve that and you back substitute. Bernoulli is similar in that it can be solved by a substitution. The Bernoulli differential equation looks a lot like a first order linear equation. Oops, sorry. But we've got this y to some power on that function on the right-hand side. Now, if y is equal to, or if n is equal to 0, then it's just first order linear. If n is equal to 1, well then this y term can be brought over to the other side and still first order linear. But if n is not equal to 0 or 1, this is a Bernoulli differential equation. And this can be solved using this method. You want to let u equal y to the 1 minus n power, and then differentiate as necessary. Substitute into the differential equation. And then after substitution and simplification, the resulting differential equation is a first order linear equation. You can solve that one with an IF or integrating factor. So this isn't, so homogeneous polar equations aren't separable, but we can make them separable. Bernoulli equations are not first order linear, but through a substitution, we can make them linear. And so those are our first 4 methods for solving first order differential equations. Now, the last method that we talked about was solving exact equations. Exact equations were a little bit different. We said that a differential equation of this form, m of xy times dx plus n of xy times dy equals 0, is exact if the partial of m with respect to y equals the partial of n with respect to x. Now remember what exact means. When we say that it's exact, what we're saying is that this left-hand side is the total differential of some function f. And we're saying that that will actually be true if the partial of this function with respect to y is equal to the partial of that function with respect to x. Now we solve this by taking antiderivatives. So if this is actually equal to that, then this is the partial of little f with respect to x. To get f back, you take its antiderivative with respect to x. Over here, this should be the partial of little f with respect to y. If you take the antiderivative of that, you should get f back. So you're going to have 2 different versions of the function f. Then you have to match them. They are actually identical to each other, but you won't be able to tell on the surface. They're going to look different, but they're actually identical. You're going to have to arrange the pieces and match the pieces so that you can show that the function that you get when you anti-differentiate this guy is equal to the function that you get when you anti-differentiate that guy. That's going to give you f of xy, and the solution is a level curve of this function of two variables. It's f of xy equals k. All right, so those are our 5 methods for solving differential equations. Now, before we get started on applications, I want to review this pre-calculus concept of variation because it's so important. It's going to allow us to translate English sentences into differential equations. We've reviewed all of these methods for solving first-order differential equations because when we're working application problems in this unit, all of those application problems will feature differential equations, and you're just going to solve them using one of these methods. So we have to be familiar with all of the methods, and then using this, we have to know how to set up the problem. So we need to know how to read the problem statement and write down the correct differential equation. We'll look at some familiar applications just so that you are aware of what's out there. And there are so many applications of differential equations. That's why ordinary differential equations is required for everyone when you are a STEM major. I think almost everyone has to take differential equations because there are so many applications. There are so many ways that derivatives of quantities are related to the quantities themselves, as we'll see when we look at the application problems. And then we'll do at least one example and maybe 2 examples if we have time. I have a feeling we're only going to do 1 example because this video is already getting long and we haven't talked about variation yet. So let's start talking about variation. So here are some sentences and how we translate them. We say that y varies directly as x, or y is directly proportional to x. If the following is true. If y is equal to a constant times x, and this constant k is called the constant of proportionality. Now, it looks like you've got 3 variables here, but you really don't. You might not know what k is, but k is a constant, it's just unknown. We're thinking of x is varying and y is varying, so k might be 2. Might be that every time x goes up by 1, y goes up by 2 if k is 2. But we don't know that constant. We call that the constant of proportionality, but this is saying as x goes up, y goes up. As x goes down, y goes down, because we're dealing with something like this. This is provided that that constant of proportionality is positive, I guess. So we have a positive slope. Anyway, that's what directly proportional means. Now, if you see this, y varies inversely as x, or y is inversely proportional to x. When that means that y is equal to a constant divided by x. If you see y varies jointly as x and z, or y is jointly proportional to x and z, what that means is that y is directly proportional to both of them. So it's probably just exactly what you would expect. Y is equal to k times x times z. So these are really important. Whenever you're looking at the problem statements for your word problems, typically this y is a rate of change. So anytime you see rate of change, you want to think of derivatives. So if someone says the rate of change of blank, and let's say we've got temperature, just for example. And this rate of change is proportional to something. You would say, well, this is, whenever you see rate of change, you're thinking instantaneous rate of change because we're in differential equations class. And we're saying that temperature has an instantaneous rate of change of something. And so that's the change in temperature with respect to something. Now, in the absence of more information, if they don't say with respect to something, they say just rate of change of temperature is proportional to, and so on. Most of the time, you can assume that that variable is changing with time in the application problems. You've got to look at the context, see what the problem statement says, and see if they're talking about how this changes as time changes. Most of the time, that's true. Occasionally, it's not. Let's say you're talking about the rate of change of temperature with respect to some spatial variable x. So maybe it'll say the rate of change of temperature with respect to position x is given by this, the derivative of t with respect to x. So that's how I would translate this part. So whenever you see rate of change, think derivative, and it's going to be the rate of change, the derivative of whatever this is, usually with respect to t, but occasionally with respect to something else, and they will have to tell you. So it'll say the rate of change of some variable with respect to some other variable. This is the variable that goes in the numerator, and this is the variable that goes in the denominator. So if I'm looking at the rate of change of temperature, that's dt. With respect to position, that's dt dx. If they just say rate of change of temperature, in the absence of more information, probably also implied by context, I might assume that that's dt dt. In general, the rate of change of something with respect to something, it's the derivative of this variable, whatever it is, with respect to this variable. Or we're talking about this quantity temperature with respect to position, it's dt dx because t is representing temperature and x is representing position. Okay, I think that's enough to get us started. Now let's look at some examples. We're going to practice translating English sentences into differential equations. So let's say we're told that the rate of change of the population at time t is equal to the product of the current population and the difference between the birth rate beta of t and the death rate. Delta of t. Well, in order to translate this, just being very careful, I'm taking each part of the sentence one piece at a time, and then I'm using that to write down the differential equation. So first it says the rate of change of the population at time t. So I will assume that that's change in population with respect to time. Now you could use any variable you want. I just used capital P for population. Is, or is equal to, that's going to become an equal sign. It's going to be the product of, so we're multiplying, the current population, so that's P, and the difference between the birth rate and the death rate. The difference between the birth rate and the death rate is the birth rate minus the death rate. So now I've got this differential equation. You've got functions of t over here and a function of p, but I've got a product. So I could divide by p and multiply by dt. This is separable. So if this came up in a problem statement, I would translate this way. There'd probably be some more information where they gave me the actual birth rate and the death rate. They gave me the initial population, and then I used that birth rate, death rate, and initial population to find the population as a function of time. Now let's do another one. Let's say we're told that the number of interactions between two groups of size A and B respectively is equal to A times B. Okay, and then they give us the rest of this. They say the infection rate or rather than calling it the infection rate, let's say it this way. A virus is spreading at a rate proportional to the number of interactions between those with the virus and those without the virus. Okay. So they give us two pieces of information here. This second sentence talks about a rate. The virus is spreading at a rate proportional to something. So we've got the rate a virus is spreading, that's the first part. And that's proportional to, so it's going to be equals a constant times the number of interactions between those with the virus and those without the virus. Okay, now we have a more information here too. I need to express this number of interactions between those with the virus and those without the virus algebraically, but I need some variables. Let's say that X is the number of people with the virus at time t. And let's say that the total population is n. Well, if the number of interactions between those with the virus and without the virus is the product of the number of people with the virus and the number of people without the virus, I can use that to write down the right-hand side of this differential equation. So if I'll have the number of people with the virus is X, and then the number of people without the virus is everyone else. If there are n people in the population, n minus X people don't have the virus. Now, this is not taking immunity into account or anything like that. So that's the right-hand side. Now, the left-hand side, you might think is a little tricky. It says a virus is spreading at a rate. You'd say, well, what does that mean? It's the rate of spread. How do you measure the rate of spread of a virus? Well, if X is the number of people with a virus at time t, dx dt would be the rate of spread, because that's the number of people getting the virus per unit time at a particular time. So that's a measure of how much it's spreading. So we have this. Now notice that there's no T on this side, so this is separable. So we've got a population growth model, and we've got the spread of a virus right here as two applications of first order differential equations. Both of them happen to be separable. This next one is called Newton's law of cooling. It says the time rate of change of temperature is proportional to the difference between the current temperature and the temperature of the environment. And let's represent that temperature of the environment with a letter E. So let's translate this. Time rate of change of temperature, that's dt dt, that's equals, it's proportional to, means K times the difference between the current temperature and the temperature of the environment. So if T is the current temperature and E is the environmental temperature, this is our differential equation. This is called Newton's law of cooling. Now, in general, this is a first order linear differential equation. But if the environmental temperature is constant, then this is separable. So we'll just look at it in two cases. We'll say if E is a constant, so let's say you're talking about room temperature and the temperature in the room stays constant, then the dE is separable. But if the temperature changes with time, then the dE is first order linear and it can be solved with an integrating factor. And there are so many more. We just looked at 3 examples. I made another video over this. I started to make a video, and then the example problem I chose was extremely long and extremely algebra intensive, very tedious. And after the 3rd page of solving this differential equation, I said, you know what, my students are going to want a simpler differential equation. So I decided to remake the video, but I want to show you what I did when I made the last video. Here are more examples. I'm not going to write them down again because I've already written them down. But these 3 actually all are the same mathematical model. They just look different because of the application. So this one says the rate of change of the amount of a radioactive isotope present at time t, that's the change in the amount per unit time, is proportional to, that's equal to, the current amount. So it's going to be a constant times A. And the constant of proportionality, is negative kappa, where kappa is the decay rate characterizing the isotope. So this is a separable differential equation. You're saying a derivative is equal to a constant times the original function. So the solution to this is an exponential function. So this is exponential decay, and it's going to be e to the negative k times t, because the derivative of e to the negative k times t is negative k times e to the negative k times t. That works. And you're also going to multiply by a constant. It would be a constant of integration initially. Okay. Compound interest works exactly the same way. The rate of change of the sum of money in savings is proportional to the current amount you have in savings. If you have more in savings, you're making more interest. If you have less in savings, you're making less interest. But that amount is proportional to the amount that you currently have in there, and that rate, the constant of proportionality, is the interest rate R. That's separable. And then we've got another population growth model. This one always makes me think of bunnies. So it says if you've got unlimited resources, plenty of land, plenty of food, plenty of water, everybody has everything that they need, and you got a little population of bunnies, the rate of change of the population is proportional to the current population. So you start with 2 bunnies, and then they have babies, and then those 2 bunnies have 4 bunnies, and then those 4 bunnies have 8 bunnies, and it just keeps going and going. That's what you have right here. So this is a separable differential equation as well, where the rate of change of the population is equal to the current population, and the solution is e to the kt. Now, this model is important enough that I wanted to show it to you as well. It says if the environment can sustain a maximum population B, and we call that population the environmental carrying capacity. The rate of change of the population, that's dp dt, is jointly proportional. So that means it's going to be a constant times a product proportional to the current population, so that's P, and 1 minus P over B, where P is the current population. So we get this. Now, in order to analyze this and make some sense out of this differential equation, I wanted to show you what some typical solution curves look like. The population is never going to be negative, so I don't ever have to worry about having curves down here. But the population could be 0. If the population was 0, the rate of change would be 0. And I think that makes sense. If there is no population, it's going to stay at a steady 0. It's not going to grow from 0 to something else. Or if the population is equal to B, B over B is 1. 1 minus 1 is 0. So the rate of change would be 0. So we'd have a solution curve that looks like that. Now, I think that makes sense because this is what B is. B is the maximum population that an environment can sustain. So let's say that that environment can only stand to take care of, let's say, 5,000 bunnies. You have 5,000 bunnies on this island. The birth rate and the death rate are going to be exactly the same, and they're going to be 5,000 bunnies all the time. That's what this says. If you're at environmental carrying capacity, you're going to stay at environmental carrying capacity. Of course, this is an idealization, but you get the idea. This is called a logistic growth or logistic population growth. Now, the more interesting cases are when that population is less than the environmental carrying capacity or when it's greater than the environmental carrying capacity. So let's say you start with an initial population that's small and positive, but it's significantly less than that environmental carrying capacity. So P is small compared to B. If P is small, compared to B, then P over B is nearly 0. So in that case, dp dt is approximately equal to K times P times 1, because this is nearly 0. So at the beginning, when the population is small compared to the carrying capacity, it looks like this. It looks like that exponential growth at the beginning. And then there comes a point when the population is still growing, but the growth itself starts to slow down. In calculus 1 terms, the graph goes from concave up to concave down at this point. We call that an inflection point. So it's still growing, but it's not growing as fast as it was growing before. Here it was growing, and it was growing at a positive rate. Here it's growing at a negative rate. I know that might be a little bit confusing. Just think of it in terms of the first and second derivative. But when the population is small, this is like nearly exponential growth. And so we see this. And then as the population gets closer to B, so let's write that down. As P approaches B, and P is going to approach B from the left because it's going to be less than B. That's what we're talking about here. P divided by B would approach 1. And it's also approaching from the left because P is slightly less than B. So in that case, this 1 minus P over B approaches 0. And if that's approaching 0, that means that the slope is approaching 0. So it starts to flatten out as it gets closer to that carrying capacity. Because the environment can't sustain more population growth. So it just sort of damps out. Now, if you started with a population that was greater than the carrying capacity, let's say the environment could only stand to hold 5,000 bunnies, and then there were 5,100 somehow. Someone was like, "Go to Bunny Island, have fun," and then she, this woman puts 100 bunnies there that don't belong, and we can't sustain them. What happens is this: the population starts to decrease at that point. If we have more than the environment can sustain, the population gets smaller. Now, if you're saying, well, how is that related to this? It's a very good question. If the population is greater than that environmental carrying capacity, P divided by B will be greater than 1. 1 minus something that's greater than 1 is going to be negative. So I'll have a negative number times this positive number, which is a negative number. So the slope is going to be negative. So it's decreasing. And it's approaching this y equals b. So this is logistic growth. You can learn a lot about the solution curves just by looking at the differential equation without even solving it. Now there's no t over here. So if you wanted to solve it, you could just separate the variables, divide both sides by p times this quantity, and then you would have to use partial fraction decomposition for the expression on the left-hand side for that antiderivative. Okay, so we had looked at 7 different examples of applications and translations of some sentence into a differential equation. I want to show you a few more examples, and then I think I'll end this video, and then in the next video, we'll actually work an example problem of an application. Okay, so here is a handout that I provide for you guys on the Blackboard site. Oops, that's not what I wanted to do. Just trying to get this little bar out of the way so I can see everything. I believe this sheet has 11 applications on it. So we've talked about this population growth one. The rate of change of the population is equal to the difference between the birth rate and the death rate times the current population. We looked at populations with logistic growth just now. Radioactive decay, the amount of the rate of change of the amount of an isotope is equal to this negative decay rate times the current amount that you have. We didn't do the free fall and gravity problem, but I think everyone knows from physics 1 that force is mass times acceleration. So that's what this left-hand side says. Acceleration is the same as the rate of change of velocity. And we all know from physics 1 that the total force acting on an object, or the resultant force acting on an object, is the sum of all the forces acting on an object. So if you've got some object that's acting under 2 forces, you've got the force due to gravity acting on it, and you've also got this air resistance acting on it. Air resistance is proportional to the velocity. Then you could subtract those 2 forces, because one is opposing the other, you've got that negative sign, and you would set that equal to the resultant force, which is that mass times acceleration. So this gives us a first order differential equation involving v, and I've got dv dt right here and v of t on the right hand side. So this is a first order linear differential equation. You can solve it with an integrating factor. We talked about Newton's law of cooling already. That's on the sheet. We didn't talk about RC circuits, a circuit with a resistor and a capacitor in it. But if you just add up all the voltage drops as you go around the circuit, you get a differential equation that looks like this. Remember, current is the rate of change of the charge. So it's change in charge per unit time is current. So that's the IR right here on that far left side of the differential equation. We talked about compound interest. This loan repayment one is a little too close to home. It's talking about student loans. This is the amount, the rate of change of the amount that you owe per unit time is equal to that interest rate that you're paying times the amount that you owe at a certain time, minus M, where M might be your monthly payment. So this can help you to understand how much you owe at a certain time and how much you will owe in the future if you solve that differential equation. We talked about the spread of a disease. If you have a chemical reaction where compound A and compound B are reacting in a one-to-one relationship, so you need one of A and one of B to make C, well then in that case, you've got a second order chemical reaction that can be described by this differential equation. That's separable. And then you've got mixing problems. You see these often where you've got some tank and you've got solutions of different concentrations and they're being mixed together. Now, this is the most vague differential equation on the sheet. It just says that the rate of change of the amount of some substance in a well-mixed tank at time t, that rate of change is equal to the rate that's going in minus the rate that's going out. And the rate going in and the rate going out are related to the concentrations of that solutions that are going in and out of the tank. So I think we'll probably do one of those problems in the next video. So that's it for right now. So far, what have we talked about? Let's see, we talked about, just trying to find the sheet. Those 5 methods for solving first order equations. Almost all of them that we saw were either separable or first order linear, but any application problem that you'll see in our class will be one of these 5, will require one of these 5 methods to solve. So it'll be separable or linear, or homogeneous polar, which can be solved with a substitution to make it separable, Bernoulli, which can be solved with a substitution to make it linear, or exact. Actually, to be honest, I don't think that you're going to see any exact equations in here. I think it's going to be one of these 4, definitely. Now we know about variation. We can talk about quantities being directly proportional, jointly proportional, or inversely proportional, and use that to write a differential equation. And we've talked about applications. So see you in the next video to do an example.